Good morning, everybody. It's Miss Pollock again with some more energy for you. So, today we're going to talk about quantitative LOL diagrams, how to put numbers onto these LOL diagrams. And in order to do that, we need some equations. So, these are the equations for you. I've made a table for you so you can refer to them. So, kinetic energy, some of you may know, the way to find kinetic energy is 1/2 times the mass times the velocity squared. The mass needs to be in kilograms. The direction of the velocity doesn't matter because you're going to square the velocity. The gravitational potential energy is the mass of the object times little g, which we know is 9.8 newtons per kilogram, and times delta y, which is the distance from whatever you decide your y equals 0 reference point is. The elastic energy is 1/2 times the spring constant times the stretch or the compression of that spring squared. And the dissipated energy is the force times the displacement of that object. A lot of times that force is friction force because dissipated energy occurs when there is friction. Another little summary that I have for you is what we call positive work or negative work. Positive work is when energy is transferred into the system. That means something outside of the system is doing work on the system. We talked about that with some of the LOL diagrams without numbers. And negative work is when the energy is transferred out of the system. The energy transferred by work is W equals the force times the displacement, where the force and the displacement are parallel to each other. E dis is not recoverable energy. That means once it is E dis, it cannot be converted to another type of energy. So again, this is just for your reference. But the real reason I'm here today is to do an example of a quantitative LOL diagram. So I have a 1,500 kilogram moving car, rolls up the hill. It starts at 20 meters per second and then it stops. So it tells me what my system is. My system is the car, the road, there's a normal force between them, and the earth is also in my system with the gravitational force. So it's moving, so I know I start with kinetic energy. It says that it's at y equals 0, so there's no gravitational energy. And it also, there is nothing deformed, there's no spring, so there's no elastic energy. So I start with kinetic energy. Let's just say 4 blocks of kinetic energy. At the top of the hill, as you can see, it is not moving, but it is above my y equals 0, so it's not moving and nothing is deformed. So all of that kinetic energy in the car was transferred to gravitational energy in the gravitational field. So I would write that is my kinetic energy in the car equals my gravitational energy in the gravitational field. So the question is, how far up the hill did it go? Well, I can find my kinetic energy. Kinetic energy is 1/2 mass times the velocity squared. So my kinetic energy is 1/2 times 1,500 kilograms times 20 meters per second, and I square that. So my kinetic energy is equal to 300,000, and the unit for energy is joules. But I know that equals Eg. And I know that Eg equals mg times how far it goes up. That's what I want to find out right here, is this delta y. So I can put numbers in here. 300,000 joules equals my mass, 1,500 kilograms, times 9.8 newtons per kilogram, times my delta y. Now all I have to do is some algebra, I can find out that my delta y is 20.4 meters. That means from the reference point right here at y equals 0, it went up right there, my delta y, 20.4 meters. Can't forget the unit there, meters. All right, there you go. Now that we've practiced quantitative free body or quantitative LOL diagrams, that's what we'll practice next time I see you. Have a great day.